mechanics. So we are going to discuss some connection of the previous video, integration with the Newtonian mechanics. So what we did in the previous lecture, we show that integration of A cross d square A dt square dt is in fact A cross dA dt and plus some constant. So this result, we will follow this result in the Newtonian mechanics. Let's see. So the equation of motion of a particle P of mass m is given by, this is equation of motion. In fact, this is equation of Newtonian mechanics because m is mass of the particle and this is the velocity, so this is mf, force, which is a general function of r in the direction of r. This r1 is the unit vector along r, along this r. Okay, where r is the position vector of P measured from origin O, r1 is unit vector in the direction of r. F of r is a function of the distance of P from O. Okay, show that r cross dr dt is equal to c, some constant vector. So that is the main result, and that is connected with the previous integration. Interpret physically the case when f of r is negative and when f of r is positive for this equation. This one, when r is negative, what will happen to the dynamic, and when r is positive, so what is the dynamic then? Interpret the result A geometrically. We have to geometrically give some interpretation of this equation. Describe how the result obtained related to the motion of the planet in our solar system. How this is related with the motion of the planet. Okay, so let's start the calculation. So this is the same, I'm writing the same equation again over here. M d square r dt square is equal to f of r r1. This is the unit vector along r. So if I multiply this equation by r, I take the cross product, taking the cross product, and this m is constant, so I am take it common or out of the cross. So this is dr dt square is equal to f of r is a scalar function, so r vector will be crossed with r1. So this is unit vector along this r, that means the cross product will give me 0 on this side. So you see we have m r cross and that is equal to 0. So dividing both sides on m, we have this equation r vector dr vector dt is second derivative square equal to 0. So integrating both sides with respect to t and using the result, so I am writing again integral of a cross second derivative of a with respect to time. When I integrate this, I get this a cross dA dt and say plus some constant of integration. So when I integrate this, so that is the same case that I will integrate r cross d square r dt square and dt, and on the right side I will get a constant vector, constant of integration. But when I integrate it, what I will get r cross the first derivative of r dt, and that is some constant. So this is the relation we needed, you see in the previous slides. So we have to show that r dr dt is constant, where c is a constant vector. So we derive this relation, and this quantity is constant. If we have dynamics of this equation, under the dynamics of this equation, this quantity is remain invariant, it is constant. So interpret physically the case when f of r is negative, and so I done the case number 1. Now I will discuss this equation for negative f of r and positive f of r. So when f of r is negative, that means the force is attractive. So you see in the question we have 2 point P, point O and P. So the force is attracted toward the center in this case when this is negative. But when this is positive f of r, then the force is repulsive from the origin. So I'm writing the equation again, m d square r dt square d square r dt square is equal to f of r in r1 direction. R1 is unit vector along r. So when this f of r is negative, the force is toward the center, and when this is positive, the force is repulsive. So in one case it is attractive, in the other case it is repulsive. Okay, so that is the second part. Interpret physically the case f of r negative and f of r positive. So in this case the force is attracted toward the center, and in this case the force is repulsive. So you see we have origin and point P outside. So when f of r is negative, the force is attracted toward the center, and when the force is positive, the force is away from the center. That is repulsive force. So that is the physical interpretation of the two cases. Interpret the result in A geometrically. So now let interpret it geometrically. So I am writing here, this is the part A. This is part A. This is part B. And let part C, do the part C over here. Geometrically, so you see we have a point O, and outside point, let's say I am taking this P point, but the particle is moving, so I am taking another point. So if the particle is moving in a curve, then let's say this is M. So the particle is moving in a curve path. Let me write it again. That is a curve path, and this is the straight line. Okay, so this is R, vector R up to here, and this distance is delta R. So you see, if I take the quantity 1 over 2 R cross delta R, what is this? R cross delta R is the area of the parallelogram whose parallel side is R and R and delta R and delta R. So if I complete it, so that is a sort of parallelogram, the area of which is R delta R, but when I divide it by 2, I only interested in this area. This area of the half of the parallelogram is a sector, you can say. Half of the parallelogram area. Now if I divide it by t this and take the limit delta t tend to 0, this become 1 over 2 r cross dr dt. So you see this value is 1 by 2 r cross v, and we prove that this value is constant. In the previous case we proved that this value is constant. You see it in the previous slide. In part A we see that this value is constant. So 1 over 2 times a constant is again a constant. Okay, so what that mean? This is area. That mean aerial velocity. So this is aerial velocity. Aerial velocity is constant. So I am writing over here aerial velocity. Aerial velocity of the motion is constant. This is not in constant. So aerial velocity is constant. What this mean? This mean that the area implies the area swept by the body is constant. That means sweep equal area in equal interval of time. Sweep particle P, sweep equal area in equal interval of time. Equal interval of time, which is one of the Kepler law, Kepler says that the planet moves around the sun in elliptic orbit, and the planet sweep equal area in equal interval of time. So this is aerial velocity. Aerial velocity is constant. That means area, the ratio between area and time remain constant for a planet. That means equal area covered by the planet in equal interval of time. In other words, particle P sweep equal area in equal interval of time. So this is Kepler law, one of the 3 Kepler laws. So that is geometry of that equation. That is the conclusion of the geometry of the result A. In result A, we show that r cross dr dt is constant. So the geometrical interpretation of this result is the planet, or let's say the point mass P sweep equal area in equal interval of time. We can deduce another thing from here, that is conservation of of angular momentum. You see, r cross v, this is in fact v, is constant. So if I multiply this with m, both side is again constant. It will be again a constant vector. So let that vector be C2. So what is this now? This is r cross p, and which is a constant vector. That means conservation of angular momentum. So the conservation of angular momentum hold in the dynamics of the equation given in this problem. So the conservation of angular momentum. So conservation of angular momentum and the physical interpretation is geometrical interpretation is this, that equal area covered by the particle in equal interval of time. So these are the conclusion of the equation. Now the fourth one, describe how the result obtained relate to the motion of the planet in our solar system. So we already discussed it that in fact the particle sweep equal area in equal interval of time, and it is one of the Kepler law. But before this law, the Kepler says that the planet is moving in an elliptic orbit. The planet is moving in elliptic orbit around the sun at one focus of the ellipse. So this the mechanics of this equation, dr square dt square is equal to f of r f of r r1, where this is unit vector along r. This equation, so we conclude from this equation that the angular momentum of the planet is conserved, and the planet sweep equal area in equal interval of time. So the fourth case we can connect with this equation, that the planet moves in elliptic orbit and it sweep equal area in equal interval of time. In this scenario, the sun is one focus in one focus of the ellipse. So that is the connection of this equation with the planetary motion. In the next question, we will see that this equation, when we put f of r is as the gravitational force, represent elliptic orbit. So this equation, in the next question we are going to prove that this equation is the solution of this equation is elliptic orbit. So that is the confirmation that when a body obey this equation, for f of r to be the gravitational force function, So the body should move in an elliptic orbit. So that is the next task. Show that the path of the planet around the sun is an ellipse with the sun at one focus. So that is the next task we have to do. So we have to make the plot again. We have sun here. The planet moves in this path. So writing again this equation, d square r dt square. Now I will particularly put the gravitational force of the sun on the planet. So here is r square and in the direction of r1. So the planet has mass the small m and the capital M represented the mass of the sun. So this is equation of the, you say, a Newtonian mechanics per gravitational force. Okay, let's show that the solution of this equation or the path followed by the particle which obey this equation is in fact elliptic orbit, elliptic path. In other words, the solution of this equation represent elliptic path which is followed by the planet around the sun. So for that we have to write this equation in the velocity form. You see, this can be written as dv dt is equal to minus g capital M over r square in the r1 direction, where r1 is the unit vector along r. Where you see what I did here, I put dr dt as v. So one derivative from here converted into v and the other is d by dt. So that is again this equation. Now in the previous question we show that r cross v is a constant vector. R cross v is a constant vector, so I name the constant vector as h. Now r can be written as magnitude of r in a unit vector along r. So when I differentiate this vector dr dt, so I will use product rule on the left, that is dr dt in r1 direction plus r magnitude dr1 dt. Okay, but we see that this vector is v, so this implies this is v, velocity v. Okay, so let's try it again, the same thing, dr dt r1 plus r plus r dr1 dt. Okay. Now the H vector is r cross v. R cross v. So we have the value of v. So r can be written in this way: magnitude r1, that is, I write only this r in the magnitude form and the direction form, and then across v. So what is v? V is here, that is dr dt r1 plus r dr1 dt. You see, when you cross r1 to r1, it is 0. r1 cross r1 give me 0, and then I will multiply this r with this, so that is r square, and direction r1 and dr1, this is vector. Okay, so I left with the first term is 0 because r1 cross r1 is 0. So I left with the second term, and that will give me r square r1 and dr1 dt. So I left only with this term multiplied with this, but cross product is there. We have a cross product over here. Okay, this is r cross v. The value is here. Now when I multiply this h with, let's say, equation 1. So what I am doing, 1 cross h, take the cross product of 1 with h, so that is dv dt cross h, and on the left side what is the value of dv dt? That is this value, that is minus gm over r square r1. So I am writing here the value of dv dt, that is gm over r square r1, and cross h. So the value of h is here, that is r square r1 cross dr1 dt. So you see, this r square is cancelled with r. So I left with 3 vector in cross and a constant minus gm and what is left here, that is r1. So r1 cross r1 cross dr1 dt. So this is vector triple product, and we see in previous lecture an identity for it. So I am calculating the value of this. So that is minus gm, that is constant value, and will apply the identity which is r1 dot r1, so that will give me 1. So I'm writing, let's write r1 dot r1 in the direction dr1 dt, but here is negative sign, this is minus, and then here is plus sign, r1 dot dr1 dt and the direction is r1 here. So I use some identity over here, and we study this identity earlier. Okay, we have a result from which this is 0, and that result is when a vector has constant magnitude, then vector and its derivative are perpendicular. So this and this are perpendicular, so the dot product is 0. r1 dot dr1 dt is 0 because they are perpendicular, and we discuss a result that when a vector have constant magnitude, then its derivative will be perpendicular to that vector. So this is 0. So I left only with this this term. So r1 dot r1 is 1 because it is unit vector, and this minus is multiplied. So gm dr1 dt, this is the value of dv dt cross h. Okay, now let dv dt cross h is equal to gm dr1 dt. Now h is a constant vector, so I can write this side as this d over dt v cross h is equal to, because when I differentiate v I will get this, but when I differentiate h, that is 0 because this is a constant vector. gm dr1 dt, so dt cancel, and when we integrate this equation we get v cross h is equal to gm r1 plus some constant of integration. So let's say this is equation 2. Now take the dot product of r with equation 2. So that will give me r dot v cross h is equal to, you see that this r can be written, so gm first I am writing this r, so that is r in r1 unit vector, and dot with this r1, and plus r dot p. So this r1 dot r1 is 1, and this is scalar triple product of 3 vectors. So I can write this r cross v interchanging the cross and dot h is equal to, this is GMR only, this R is magnitude, and R1 dot R1 is 1, and I can write this length of R, length of P cos theta, where theta lies between vector R and P, vector R and P, vector R and vector P. Okay, but you see this value is, I take this value as h from the beginning, so h dot h is equal to, I can take R common, so this is GM plus P cos theta. So h dot h is h square. So this is h square is equal to R GM plus P cos theta. So R is equal to h square over GM plus P cos theta. I can write this equation as R is equal to h square over GM 1 plus P by GM cos theta. This is cos theta. Comparing, let's say this is equation 3, comparing this with equation 4, R is equal to A 1 plus eccentricity cos theta. Okay, this is the polar form of the conic section for epsilon, for different value of epsilon. If epsilon is 1, it is parabola. If epsilon is less than 1, okay, less or 0, less or equal to epsilon, less or equal to 1. Oh, is strictly less than 1 and is strictly greater than. So in this case it is ellipse. Epsilon is equal to 1. This is parabola. This is the ellipse case. And if it is greater than 1, that is hyperbola. So this is exactly this form. A is h square over gm and p over gm is epsilon. That is eccentricity of the path. But we see that the planet moves in closed path. Ellipse is not closed. Hyperbola is not closed. Ellipse is closed path. And we know that planet moves in closed path. So the conclusion is that this path should be ellipse because the planet moves in elliptic orbit. This is the solution of the given equation. This is the solution of the given equation and it is ellipse. This is an ellipse in which the planet moves. So I am writing this result again. So the solution of the given equation is R h square over gm divided by 1 plus p over gm cos theta. So this is equal to a over 1 plus epsilon cos theta. A is equal to h square over gm and epsilon is p over gm. So this should be ellipse because the planet moves in elliptic orbit. That's